Okay, so the next example here, calculate the output phase angle for each of the circuits. So we've got two circuits here. One of them already has the reactance, the reactive inductance calculated. The other we will have to calculate. So we're looking at calculating the output phase angle. So for the lag circuit, we're going to calculate, since we have X sub L and R available, it's just a simple matter of taking the inverse tangent of 5K over 15K. The K's cancel out. And when we take the inverse tangent of that amount, we get minus 18 and a half, or 18.4 degrees. I know sometimes I give you the numbers wrong in here when I'm reading them. Sometimes my mouth doesn't know what my brain is saying, so I'll try to get it right. 18.4 degrees, so don't fret. The output lags the input then by that 18.4 degrees. So for the other part, now we have to calculate the inductive reactance. So for this one, X sub L is equal to 2 pi FL. We end up with 628 ohms. Again, run that through the expression. You'll notice here we've got the negative sign, and therefore you'll notice that the value here is flipped. Instead of R over XL, we have XL over R. So minus the inverse tangent of those two values gives us a minus 32.1. So the output lags the input by 32.1 degrees. The input voltage shown, okay, has an RMS value of 10 volts. We're to determine the phasor expression for the output voltage. Draw the waveform relationships for the input and output voltages. The phase angle minus 32.1 degrees and X sub L is equal to 628 ohms. So we're just using the previous values. So for the phasor expression of the output, V out, again, notice that capital bolded V there is telling us we're looking for the phasor expression, is equal to V out at the angle of phi. So we have R by R squared plus X sub L squared, and we multiply that times Vn and use the angle phi. So in this case, 1.0 k ohms divided by 1181 ohms times 10, which was our RMS value, and at an angle of minus 32.1, we get 8.47 at an angle of minus 32.1 degrees volts RMS. And we can see then the waveforms here. We can see that we've got the lag expression of 32.1 degrees from the input to the output. Okay, let's introduce the next section here. Ohm's law and Kirchhoff's law used in the analysis of RL circuits. Current voltage relationships in a parallel RL circuit then are examined. So again, there are our Ohm's law relationships. Again, italicized, not italicized, but bolded. And we have an example. Let's go ahead and do the example. So we've got two circuits here, A and B. Determine the magnitude and the phase angle of the total impedance. So for the first circuit A, the total impedance then, again, product over the sum at an angle of the inverse tangent of this time R over X sub L. We take the product, we take the Pythagorean sum or the vector sum here at an angle of 100 over 50 inverse 10, and we get a value of 44.7 at 63.4 degrees ohms. Again, I hope that you're going through these and using your calculator and work through them so that you understand not only the mathematical process here, but the process as it relates to your calculator. Again, start with the denominator. Once you get that value, invert it and multiply it as the product in the numerator. So in this case, Z, the impedance, is equal to 44.7 ohms at an angle, this time theta, of 63.4. For B, now we've got both values given reactive. So we've got our product over the sum here, the sum being the vector sum, and at an angle of inverse tangent 1k over 2k, the k's cancel out, so we've got a value then of 894 at an angle of 26 and a half ohms. So thus the impedance is equal to 894 ohms, the angle theta 26.6. Notice that the positive angle indicates that the voltage leads the current, in contrast to the RC case where the voltage lagged the current. Okay, when we come back, we'll take a look at this problem and drawing the phasor.